There's the different wavelets perform differently. So you can play with that, see how that works. You can see the details there on the building in the background. It changes quite a bit. Oh, this one's interesting. It's very boxy. So essentially, it's down sampling the background. Yeah, you can see these large squares essentially everywhere. I know that line is there in the original image as well, but yeah, you can see the pixels in the original image as well, but so it keeps all that information. So this one is interesting. This is 4, 5. You have more of these boxes. 6. Yeah, the box is becoming smaller and smaller. So this is interesting, but it's interesting also to see how it makes essentially a decision between which area to choose. So this is 4. So interestingly, we have big squares over here when nothing is happening, and much more smaller squares around that area. I don't know when this one turned red, because essentially it can recognize some sort of major change in there, but yeah, it's obviously over, kind of overestimating it, and the red bits here are gone. So it's actually finding. So you see, there will be more squares, more blocks, more boxes where on the lines of the image. Four, 3, 2, and it's just one box, 2. So detecting all the kind of major features in the image. 3 is working okay. Already you can kind of make sense of it. That's that specific wavelet. This is another wavelet. And yeah, this one is much worse. So essentially my understanding is it is, so each one of those wavelets is a different a waveform of a signal. And we want some information on, so leave the parameters as they are. Those are the default ones: temperature at 0.7, top P at 1, and maximum output tokens at 512. And we will generate something for image compression using wavelet transform, and we'll do the same for ChatGPT. It's a good question for ChatGPT 3 because we don't need to be connected to the internet or anything. I don't know if Clinical Camel is connected to the internet or not. It's generating much more stuff. Okay. Yeah, the board talking.
Image compression using wavelet transform is a popular technique used in image processing to reduce the size of an image while maintaining its quality as much as possible. The wavelet transform is a mathematical tool that can be used to represent an image as a combination of different scales and orientations. By using the wavelet transform, the image can be compressed by removing the less important details at lower scales and orientations, while retaining the important details at higher scales and orientations. The compressed image can then be stored or transmitted, taking up less space and time to transfer. The wavelet transform has been shown to be effective in reducing the size of an image while maintaining its quality, making it a popular choice for image compression.
Right. Last time I generated a couple of times with different settings as well. I think where we set the temperature all the way up to 1, it's actually generated something better. And now it's generating a longer response.
Image compression using wavelet transform is a technique that reduces the size of an image by removing redundant information while preserving its quality as much as possible. It works by representing an image as a combination of different scales and orientations of wavelet coefficients. The wavelet transform decomposes the image into these components, allowing for efficient compression of the data. A commonly used algorithm for this purpose is the discrete wavelet transform, DWT, which decomposes the image into 4 subbands: the approximation subband, which contains the low-frequency components of the image; the horizontal detail subband, which contains the high-frequency components in the horizontal direction; the vertical detail subband, which contains the high-frequency components in the vertical direction; and the coefficient subband, which contains the remaining high-frequency components. After the wavelet transform has been applied to the image, the coefficients in each subband are quantized and entropy encoded to further reduce the size of the data. The quantization reduces the precision of the coefficients to a lower bit depth, while entropy encoding assigns shorter codes to the more frequently occurring coefficients. The resulting compressed image can be further optimized by using techniques such as run-length encoding and Huffman coding. The wavelet transform is particularly effective for compressing images because it can capture the hierarchical structure of the data, allowing for efficient compression at different scales and orientations. Additionally, the wavelet transform is reversible, meaning that the original image can be reconstructed from the compressed data without loss of quality. This is in contrast to some other image compression techniques, such as the discrete cosine transform, DCT, which are lossy and can introduce distortion or artifacts into the reconstructed image.
Right, just generated more stuff. So if we go image compression using wavelet transform, include the wavelet type levels to check. Yeah, this reminds me. to check what this more information on those levels. This is the source code that we are using, and the levels are an input to. It's a discrete. It is a discrete wavelet transform, and the levels specifies the number of levels in the discrete wavelet analysis. Levels must be positive or greater than log ls, where ls is the length of the 1D signal or the minimum dimensional size of the 2D signal. Otherwise, you can set value to -1, which indicates that this way I set levels as the largest integer, no greater than log 2. So actually, this should be -1, and would it spit out? There's no input there that wasn't implemented, which is odd. And the wavelet, instead of, I don't know why, instead of using the wavelet input, it's using a wavelet filter. I don't need more information on why this is implemented in this specific way, and why this wavelet input doesn't go directly into the this input of the discrete wavelet transform function. I think this is an inverse discrete wavelet transform. So that's okay. I get that, and that would be the measurement for source and destination. We'll assume just calculating. That's the raw equation. Yeah, again, we said we don't like these things when it's not using the square, but that's okay. It does the job. We won't be too picky with this one. This could be cleaned up a bit to make it clearer. I don't know why. Sometimes I suspect this one happens, becomes like this weird, not cleaned up diagram, because it was, I suspect, was moved between different live view versions. That's what happens after moving it for several times. Yeah, we can save this one as is. So we have, yeah, so the levels, what is it again? A detail help, number of levels. We want to include this is a chat proxy, so image compression using wavelet transform, including wavelet type and levels in the discrete wavelet analysis. Yeah, that's a separate thing. We can have a whole paragraph just on how the performance of the image data reduction compression is measured. We also will including image compression using wavelet transform, including bits and wavelet type and levels in the discrete wavelet analysis. Let's make it 4 sentences. We'll generate this in clinical QML, and the old and GPT-3, just for comparison's sake. He originally generated all this what are called points, general overview of the steps involved. It's not about that. It's a bit overloaded. How about just try to limit it to 4 sentences. Yep, this one. Checking how many it is. 1, 2. It's 3 sentences, is it? Yeah. I don't know what's up with that. So generated 4 as requested, so it's a bit odd. But we can leave with that. Yeah, that first sentence is not great. It's using the acronym, which is fine, breaks down the image into different frequency subbands at multiple levels of decomposition. That sentence a bit well. This is a technique used for image compression by representing the image as a combination of different scales and orientations of wavelet coefficients. And that's actually looks more legit because yes, it will take the actual waveform in each wavelet and will shape it so make it larger or wider. It's actually already better than what GPT-3 suggested. The discrete wavelet transform is a commonly used algorithm that decomposes the image into four subbands: the approximation subband, the horizontal detail subband, the vertical detail subband, and the coefficient subband. I don't think we have the four. The bits and wavelet type and levels are parameters that determine the quality and compression ratio of the compressed image. So I don't know much about that. It doesn't sound great. Let's skip this one. The GPT-3, each subband contains wavelet coefficients that represent different scales of the rotation of image features. These coefficients are then quantized and encoded using entropy coding techniques to form a compressed bit stream. So it is, yeah, there is an entropy thing. I wish there was, you can regenerate. If there's a copy thing here. I just have a general sentence that that these bots use to generate text on the website, but it will be hard to keep track of which one is which. So let's regenerate both responses. We'll just keep track of them. Close that. Right, now it's actually giving me different types of wavelet names. And actually in the tool, we don't specify the names. We actually have to modify it. Might as well try to do it today.